Welcome back as we continue our study of bonding. And we talked about two types of bonding. There was ionic bonding, and ionic bonding is simply the result of an electron being transferred from typically a metal to a non-metal, and that causes the metal, sodium, to become positively charged, the non-metal to become negatively charged. A covalent bond is formed not when electrons are transferred, but rather when electrons are shared. So two fluorine atoms will share a pair of electrons. Now, in both the case of an ionic compound and a covalent bonded compound, we are seeing that there are 8 electrons that are being shared in a molecule. And 8 electrons for an ionic compound are going to be what completes what we call the octet, the 8 that chlorine wants around it, and sodium loses a valence electron, and it actually goes back to the noble gas configuration of neon, which has its own perfect octet, the S2 and the S6 in the second energy, and the P6 in the second energy level. So that's just a quick overview of our ionic and covalent bonding. So as we continue looking at bonding, let's take an example of CO2. This is work that you were supposed to have done, and figure out the number of valence electrons. Carbon has 4 valence electrons. That's because of its position on the periodic table. And oxygen is going to have 6 valence electrons, and those 6 valence electrons, sorry about that, have to be multiplied by 2 because there are 2 oxygens in the compound. So this is going to give us a total of 6 times 2 is 12 plus 4, 16 valence electrons. And that 16 valence electrons are going to have to be shared between the carbon and the 2 oxygens. So carbon will be our central atom, and with carbon as our central atom, we're going to begin to put enough electrons on each oxygen in order to give them 8. So 16 minus 4, I have 12 electrons still to place around the molecule. So I'm going to start with the oxygen on the right and give it its 6 plus the bond is 2 to give it 8. And then I have 6 more electrons to place. And when I place those 6, I'm able to observe that I have, at least for the oxygens, 8 electrons surrounding the oxygens on both the left-hand side and the right-hand side. Everything looks good until I take a look at what's going on with the carbon in the middle. There's only 4 electrons surrounding it. So as the result of that, we're going to need to go back and look at how we can make the oxygen share a pair of electrons with the carbon, so that everybody has 8 and no one is left out of the octet. So in order to do that, I'm going to need to share a pair of electrons. So what I'm going to do is I'm going to take these 2 electrons that are at the bottom and go to the eraser tool and get rid of those 2 and share them there. And then it looks like I'm going to need to do that on this side as well. So I'm going to erase those 2 there and then share that pair of electrons. So as the result of doing that, I now have 8 electrons surrounding the carbon. So 2, 4, 6, 8. Every line represents 2 electrons. And then each oxygen has its octet. 2, 4, 6, 8 around the oxygen on the left, 2, 4, 6, 8 around the oxygen on the right. So this is a valid Lewis dot structure for our carbon dioxide molecule. Now let's take a look at CO3 minus 2. Before we left last time, we discovered there were 24 electrons. And so we start with carbon in the middle, and we're going to put 3 oxygens around that and bond everything to the carbon in the center. That gives us a total of 6 electrons that have been used up to form the bonds, and that gives us 18. I'm going to once again go around and place 6 electrons around each of the oxygens, because I'm doing a little math in my head and saying 18 divided by 3 is 6, and each of these oxygens needed 6 more in order to give it the octet that it's looking for, so 8 electrons around each. So as I look, I can see that there are 8 around each of the oxygens, but the carbon only has 6 around it. So my fix for that is to share a pair with the central atom. So just by way of reminder, always complete the electrons on the outside atoms before you put them on the central atom. And take my eraser, and I'll choose this oxygen. I could choose any other oxygen, I just happen to choose that one. And I place that double bond in between this carbon and that oxygen. That will give me 8 electrons around each and every oxygen, and around the carbon in the middle I also have 8 electrons. So let me mention that if you have a polyatomic ion that has a charge, so polyatomic just means many atoms, and they have a charge, you definitely want to put a bracket around the entire structure. And then let me erase my work here to show you the last thing that you need to do. You put the brackets around, and then you're going to place the charge of the polyatomic ion outside. This indicates that the 2 extra electrons are shared by the entire molecule, not any specific atom in the molecule. So what I would like you to do is take the time to draw the structures for these atoms, and I will suggest that you pause the video right now and draw those before you continue on. If you have not stopped the video, please stop the video and draw your structures, because the next screen will show you all of these Lewis dot structures already solved. Okay, let's do a quick check of our work. CF4 has 32 valence electrons, and there are single bonds all around to the fluorines that are attached to the carbon in the center. And we'll do a check on one of the other ones just to follow the methodology once again. Arsenic trifluoride, ASF3, has 26 valence electrons. There is a lone pair of electrons on the arsenic. Otherwise, it is bonded to the 3 fluorines and single bonded to the fluorines, all with their 3 lone pairs of electrons, 6 total electrons. Going down, we have sulfur, single bonded to 2 chlorines, and there are lone pairs everywhere within that molecule. Oxygen, but 3 of them bonded together, is called ozone. Ozone has a single bond to one of the oxygens and a double bond to the other. How did I know to do that? So let me just review quickly. Oxygen is bonded to an oxygen is bonded to an oxygen. So I have drawn in single bonds, and I will subtract from the 18 4 electrons, the 2 single bonds, to give me 14 electrons still to place. So following my pattern, I'm going to do pairs of electrons on the outside atoms. Even though they're all oxygen, I'm going to start at the outside. And I've done 2, 4, 6, 8, 10, 12, and now I can go to the center. I've got 8 on the outside atoms. So I've got 2 left to place. That uses up all my valence electrons, but I don't have 8 electrons on the central atom. So as the result of that, I'm going to need to share a pair. And I could have chosen the other oxygen to share a pair from. I just happened to choose the one on the right. And there we go. The double bond gives the oxygen in the center the 8 that it needed, and each of the oxygens on either side of the central atom also have 8. So that's the methodology that we follow. And then NH4, just a reminder to put brackets and a plus sign outside of that in order to draw the correct structure. So this is how we do Lewis dot structures, and once we know how to do Lewis dot structures, we can now talk about the actual molecular structure of an atom. And the molecular structure is based upon a theory that is called VSEPR theory. And I know that it says VSEPR model, but they pronounce it VSEPR in order to make it sound a little bit easier to pronounce. So what that means, VSEPR is simply valence shell, so I'll put the V there, valence shell electron repulsion, electron pair repulsion. And what this says is those pairs of electrons, those valence electrons that are on the outermost shell that are involved in bonding, are repelling each other. So the electrons are going to push away from each other as far as possible. And when they push away from each other, what they're seeking to do is to minimize repulsions between them. So they're going to get as far from each other as they possibly can when they arrange themselves around the atom. So what we're going to do is we're going to learn how this works out in the atoms that we've already done and determine what the geometry of these molecules are. So I'm going to draw all of these structures. You should take some time right now to draw each of them so that you know that you understand how you arrive at the correct Lewis dot structure. Okay, so here are the structures of the molecules that we're going to be looking at. And right now I have drawn them so that everything is at right angles. And this would be an excellent picture of the molecules if they actually were in two-dimensional space, but they are in three-dimensional space. So as a result of that, we get a little different look, and we need to talk about a couple of concepts that are going to be important in understanding the actual shape of these molecules. And this, for carbon dioxide, shows that there is a double bond on each side of the carbon. So if I can talk about north, south, west, and east of a molecule, there are two east and west regions that are occupied with bonds, and there are two other regions, north and south, where there are no electrons whatsoever. So we look at electron regions. So we say that for carbon dioxide has two bonding regions, and we're going to go down to our table below and look at the one table down here at the bottom where it talks about the number of bonding regions. And since this molecule has only 2 bonding regions, that is, the carbon around it has just 2 areas that are occupied by bonds. Those 2 regions lead to a molecular shape, which for us is very easy to understand. There are 2 regions. There are no lone pairs of electrons. So lone pairs would be on the central atom. Are there any electron pairs there? And that means that there are 2 bonding regions, no lone pairs. The shape of the molecule is linear. So if I were to look at the molecule that I have drawn above, the bond angles in between the 2 oxygens, and this is due to repulsions between those pairs of electrons around the carbon atom, is 180 degrees. In other words, they are exactly opposite each other on sides of the molecule. Let's take a look at another example. Let's take a look at another 3-atom molecule. This one for water, H2O. Right now it looks like the molecule is linear, but it's not. You need a 180 degree angle, such as carbon dioxide has, to be linear. Let's look at the structure for the water molecule, and we notice, once again, you always look at the central atom, and there are north, south, east, and west are all occupied with electron pairs. So that means there are 4 electron regions. Okay? So there are 4 electron regions for the water molecule. So any of these 3 shapes could apply. So we need to narrow things down a little bit. How many of these regions are bonding regions? Well, if we look at bonding regions, we realize that water has 2 bonding regions and 2 lone pairs. So the water molecule has a bent or a V shape to it. So rather than being linear, this molecule actually looks something like this. The bond angle is 109.5 degrees in between the hydrogens. So the oxygen in the middle is away. And why is it pushed away from the 2 hydrogens? That's because these lone pairs of electrons arrange themselves in space. Now, I said the bond angle was 109.5. Right here it says 104.5. And we'll explain that a little bit later in class, but if you understand the bond angle of 109.5 is really involved in each of these 3 structures when there are 4 electron regions, it tells you that the molecule forms a tetrahedral shape. And now I'm trying to draw this in a 3-dimensional space, but the bond angles between all of these legs coming off is 109.5. When there are lone pairs of electrons, they take up more space. They fill this area more, and so for water, rather than being 109.5, these 2 sides are pushed together a little bit because these lone pairs of electrons take up a huge amount of space around an atom, and it causes the other 2 pairs to get in the way. So as a result of this, the bond angles get shorter the more lone pairs that you have in a molecule. So let's continue on, and I'm going to erase some of my work in order to keep the table clean so that we can look at what is going on with each of these structures. Okay, let's take a look at another 3-atom molecule. This time we're going to examine ozone. That is the O3 right here. And ozone has around the central atom once again. It has 1, 2, 3. So north, east, and west are electron regions. We count double bonds as just one electron region. So those 1, 2, 3 regions cause us to not come to this table, which is 4 electron regions, but to go down to the table below it. So the total number of electron regions is 3. Now, that means it could be either trigonal planar or bent or V-shaped. So we need to look at the number of lone pairs and the number of bonding regions. So let's go back up to the molecule and look at that. All right, so this is a bonding region, that is a bonding region, and there is one lone pair. So we have 2 bonding and 1 lone pair region. So 2 bonding, 1 lone pair puts us over here. That means that the molecule is described as bent or V-shaped. Actually, that's the same shape of the water molecule, but now the bond angles are different. So whereas I told you before we can think of this as 109.5 degrees, we can think of the 118.6 as actually 120 degrees. Let's look at the molecule and see what I mean by that. There are 3 bonding regions around the oxygen in the center. So VSEPR theory, valence shell electron pair repulsion, tells me that these 3 atoms want to be, or these 3 electron regions want to be as far apart from each other as possible. So as a result of that, if I have 3 atoms arranged around a circle, the farthest apart they could be would be 120 degrees from each other. And whether that is in 2-dimensional or 3-dimensional space, they're going to be 120 degrees apart from each other. So the bond angle is 120 degrees, but we say the shape of the molecule is based only on what the atoms are doing. And so the molecule is bent or V-shaped because of the fact that there are 3 regions, but only 2 of them are bonding. The water molecule is also bent, but it has a bond angle of 109.5. So let's go on now to our 3 attachments to a central atom, and we're going to look at SO3 initially right here. And if we look at that, there are 1, 2, 3 bonding regions around the central atom. So I think we can go back to the table we were at before. There are 3 bonding regions, no lone pairs of electron, and that leads to a shape that is known as trigonal planar. So these 3 lie all in the same plane and slightly different than the O3 below it. All of the regions are occupied with an atom. Therefore, I have the 120 degree bond angles, but the shape of the molecule is called trigonal planar because of the fact that there are 3 atoms surrounding the molecule, whereas ozone only had 2 atoms surrounding the central atom, and it had a lone pair of electrons. Remember that lone pair takes up more space, pushes the others away, and so as a result of that you get a slightly smaller angle. But for SO3, all of these oxygens are equivalent to each other, so we get a shape known as trigonal planar. Finally, for a 3-molecule atom, we're going to take a look at this NH3. This is known as ammonia. so oftentimes used in window cleaner. And the ammonia molecule has 1, 2, 3, 4 electron regions. So there's a lone pair up north. South we have a bonding pair there, bonding pair there. So let's look at our table for 4 electron regions around the central atom. And when we look, we see we have 1, 2, 3 choices. And with 4 electron regions, we are going to be able to analyze it to see that there is 1 lone pair and 3 bonding regions. That leads to what is called a trigonal pyramid. And the bond angle is once again a little smaller than 109.5 because there's a lone pair of electrons up here that take up a lot of space. So the way that we would draw that molecule is we would have nitrogen here in the middle and a lone pair of electrons taking up a lot of space up there, and then 3 hydrogens at a bond angle of 109.5. So this is a triangle. There's the base down there, and then 3-dimensionally it's a pyramid that leads up to that lone pair of electrons. Finally, our last molecule to analyze is CH4. This is methane. Methane gas is what you burn in your furnace. And the methane molecule, around the central atom, carbon, there are 4 bonding pairs. So those 4 bonding pairs bring us to this table once again. 4 total electron regions. No lone pairs of electrons on the CH4. So the shape of that molecule is called a tetrahedral. Tetrahedral, perfect bond angle of 109.5. And so the way that we indicate that molecule is we draw that lone hydrogen up on top, and then we draw these 3 on the bottom. When we're in class together, we'll work with model kits in order to see these pictures drawn out in 3-dimensional space using those models. So before we meet together, what I would like you to do is to do this section, which deals with electronegativity, and this follows up on trends that we learned about on the periodic table. You know a little bit about this already, so if you could just complete this page of the worksheet, we will follow up in class on it. Let me point out something that should be helpful to you as you go through this. If you remember talking about the size of atoms, the smallest atoms in terms of atomic radius are in the upper right-hand corner of the periodic table. Now, the noble gases do not have this property called electronegativity. And what electronegativity is the ability of an element to attract electrons. Okay? So if I have 2 atoms, let's say hydrogen and fluorine, hydrogen has an electronegativity of 2.1, fluorine has an electronegativity of 4.0. In a situation such as this, the fluorine is better at attracting electrons to itself than the hydrogen. So these 2 electrons in the bond of H and F tend to go toward the fluorine. I liken it to sharing with my brother or sister who were older than me. Anytime we shared something, I'm pretty sure they got the biggest portion of whatever we shared, as long as it wasn't carrots or broccoli. So the electrons are closer to the fluorine than they are to the hydrogen in the bond. So here, instead of this being equally distributed, you will see that the electrons in the bond, and I'm drawing it fatter on the right-hand side closer to the fluorine, they tend to go toward the fluorine, which makes it slightly negatively charged, and that's a lowercase Greek letter delta, and the hydrogen ends up being lowercase Greek letter delta, slightly positively charged. We call that a polar bond, and it leads to, in the case of HF, a polar molecule. So what I want you to do is understand electronegativity on the table, and you'll realize that the smallest atoms have the highest electronegativity. So the trend on the periodic table is as you go from lower left to upper right, electronegativity increases and the atomic size decreases. So electronegativity increasing and the atomic size decreases. So once you are done with this, then we'll be able to move on to the next section. Please complete the work here. And then we're going to begin talking about polarity once we get to class, and how electronegativity and the atomic shape play into the polarity of a molecule.